Lesson 40 means you're at the end of the first half of Shormann Calculus 1. You come a long ways. Here we're looking at definite integrals as sums of infinite series. And in Lesson 36, that mentioned that here in Lesson 40, we'd make that jump from delta x to dx. And that gives us the exact area under the curve for a function f of x that's continuous on some closed interval a to b. So in exploring derivatives in lessons 17 and 18, we followed a similar trend, right? We first observed how derivative means slope by studying rates of change for larger delta x values. Then we applied the limit definition of a derivative to obtain exact answers that result when delta x becomes dx, the infinitesimal. For simplicity's sake, instead of saying delta x becomes an infinitesimal, that whole phrase there, we just write this. Delta x arrow 0, delta x approaches 0. And we assume the infinitesimal equals 0. We assume that, right? It doesn't. It's a real tiny change, right? It has to be a real tiny change. It's so small, though, we can assume it equals 0, even though in the back of our mind we're saying, well, no, it's not 0. That type of trend, looking at how delta x becomes an infinitesimal and what's happening there and how we get our most accurate answer when that happens, we're following a similar trend for integrals. Now we'll use infinite series, those formulas from lesson 23, like for x and x squared and x cubed, to find exact areas, also known as definite integrals. A simple way to distinguish between like a definite and an indefinite integral is those indefinite integrals that have that plus c on the end, right? And they have a formula, a function, a symbolic form that goes with them. Definite integrals, they're about a number, finding a numerical result. Now, the thing to notice and the thing to appreciate later in lesson 43 is that these infinite series, using them to find the exact answer of the area under a curve, this is the hard way to find definite integrals. We're not going to do a lot of them, though. It's good for you, though, to see how this works, to be challenged by this, and provide as much evidence as possible for the faith-based leap. You have to make that faith-based leap here, right? As delta x becomes an infinitesimal, you just trust that that equals 0, but it doesn't equal 0, and that it's giving you your exact answer. So in lesson 43, that's when we'll start using the easy way, and we'll calculate definite integrals by applying the indefinite integral formulas that you learned about first in lesson 33. So enough talking, let's get started here. Look at example 40.1. It says use right sums to find the exact area under f of x equals x on that interval 0 to 2 by allowing delta x to go to 0. Become an infinitesimal. That also means your number of subintervals goes to infinity, right? Because if delta x has to become an infinitesimally small dx, that means you end up with an infinite number of rectangles that you're summing. First, and you could do this on your graphing calculator if you wanted to too, just calculate that integral. You can actually calculate the exact answer. So we've got an xy axis, we're going out just a few here, and we want to know that integral from 0 to 2. So y equals x, f of x equals x, that's just a line going up like that, right? And so really what we want to do is find that area under the curve right there. And so it's got a width of 2, a height of 2. It's just the area of a triangle, right? 2 times 2 over 2 equals 2. There's our area. For a linear pattern like that, we can find an exact area under the curve without having to do any integration at all. But we've been asked to do this the hard way, using infinite series, so let's do that now. And first what we want to do is apply the limit definition of an integral from lesson 35. We'll apply that to f of x and replace that delta x going to 0, this part, replace that with n approaching infinity. That it means the same thing here. So delta x is a constant also. We can factor that out of our limit definition for an integral. So think about it. It's limit as delta x goes to 0 of the sum, that's our limit definition, I equals 1 to n of f of xi delta x. Okay, we can factor a delta x out because that's a constant, and we'll say limit delta x approaches 0, and then we'll move that delta x out. Delta x times the sum I equals 1 to n of f of xi. And in terms of n, rewrite it, limit as n, the number of subintervals goes to infinity of b minus a over n. That's how we find delta x, right? That's what we've been doing a lot of lately. That delta x is b minus a over n. That shouldn't be a surprise to you. Of I equals 1 to n of what is our function here? F of x equals what? X. So we just say x sub I. Okay? What is b minus a? It's 2 minus 0, right? It's 2. So simplify this a little bit more. Limit, I'll put an equal sign here, limit as n approaches infinity of 2 over n. Sum I equals 1 to n of x sub I. Now you might see that sum x right there and you think, okay, this is the sum of x formula from lesson 23. I'll just substitute that in now and be done. Well, no, we need to think about these subinterval i's. Here's a key part of this problem. Use right sums. Okay, so we still have to think rectangles here. So that means the first one's going to be delta x over. That's where we'll start. So 0 plus whatever delta x is. Delta x is 2 over n. So just thinking of not all the limit stuff, not the 2n part, but just the factor, and that is what this is. It's a factor, the sum I equals 1 to n of xi part. How does that apply here? Well, the first term is going to be 2 over n. Because the input is 2 over n, the function is just x. The input equals the output, right? And then the next one, we got to go over by 2 over n to get to the next rectangle. So it's just going to be 2 times 2 over n. And then the next one would be 3 times 2 over n. And we're going to erase this xy axis over here because we don't need that anymore, and just be thinking about that pattern. What is the pattern that we have here? Plus 4 times 2 over n, and so on, right? I'm just going to keep going with that. So we could simplify that to factor out a 2 over n times 1 plus 2 plus 3 plus 4 plus so on. What is that? That's 2 over n parentheses sum of x, right? From x equals 1 to n. Now, that part right there, we can use the formula on. 2 over n. What's the formula for sum of x? It's n times n plus 1 over 2. If you don't remember that, go back and look at the lesson 23 rules. That's the formula for sum of x from I equals 1 to n. Keep up with me here. This just equals this xi, sum of xi factor right there. Go back now to the limit definition. Limit as n approaches infinity of 2 over n times all of that, 2 over n. We're just replacing sum of xi now, right? 2 over n times n plus 1 over 2. Cancel a couple of things there, a 2 over 2 there, and n over n. And we can rewrite this as 2 times n plus 1 over n, which is the same thing as 2n plus 2 over n, which equals 2 plus 2 over n, right? If we broke that up into two pieces there, 2n over n is just 2 plus 2 over n. Now, the whole thing here is as n approaches infinity. So this right here, bottom right corner here, that becomes infinity. What's 2 over infinity? What can we assume that equals? 0, right? What are we left with? We're left with right here 2. Same thing we started with the triangle area, right? On the practice set, I'd probably just ask you, like on one like this, just, what does that equal? I'm not going to ask you like what the definite integral is, but I'll just ask you to evaluate it down in terms of n. So either like a 2 times n plus 1 over n or something like that is what your answer would be for this, not that it equals 2, because you can just do that with a graph, and you can do that on your graphing calculator, right? I want to see that you know how to use this limit definition and use the formula for the infinite series. Know how to use that properly. Problem 2, repeat that last example, just this time we want to use left sums instead of right sums. So we're always kind of starting, instead of at n, starting at n minus 1. Instead of starting at I, we're starting at I minus 1. That's the idea, the big idea that you need to get across in this. So let's not start from the very beginning here, but let's start with our summation. That was our big part, our sum of xi, that we had to kind of think about how that worked. So let's start there. And we know it's same interval, so we're factoring out a delta x at the beginning. The delta x is equal to 2 over n. We know that part already. Just that sum of xi, that subinterval part, is what we need to consider here. And instead of xi, this time we have xi minus 1. So, I mean, just think about Riemann sums, left Riemann sums. What would that first one be then? It would be 0, right? And input of 0, output of 0 for f of x equals x. And then the next one, we'd be at I equals 2, so that'd be 2 minus 1 x sub 1. That one is going to be over delta x, so that'd be 0 plus delta x. So there we'd have to say 1 times that delta x is 2 over n. And then just follow that pattern. 2 times 2 over n. We just keep adding on delta x, right? That's how we get those rectangles to work. And then another delta x would be 3 delta x's. And so on. Again, we can factor out a 2 over n here, right? 2 over n times 0 plus 1 plus 2 plus 3. What's that looking like? It's looking like that sum of x again, right? 2 over n, turn that into a sum from I, or actually in this case what we want to think about is for x itself, for x equals 1 to n of not x, because if x equals 1, then we just have a 1 there. We need to start with a 0. So this has to be an x minus 1. Okay, now watch this. What's our summation formula? Our summation formula is n, when it's just x by itself, it's n times n minus 1 over 2. Now if we changed that from x to x minus 1, that means n has to go from n to n, change it to red here just so you can see it, to n minus 1. See where I'm changing things. And then the other n in n minus 1, that has to do the same thing. And actually it's n times n plus 1 right here, right? That's the formula, n times n plus 1 over 2. So here we have to do n minus 1 again, right there, plus the 1 on the end, all over 2. So that gives us 2 over n parentheses n minus 1 times n minus 1 plus 1, that's just n, over 2. That's our sum of xi part, right? Now we have to go back to the limit definition and substitute that in. Limit as n approaches infinity. Same thing we did before in problem 1 of 2 over n sum I equals 1 to n of x to the I minus 1, because it's left sums this time. So that equals 2 over n times 2 over n. So remember here, this part right there is this part. Those two are the same thing. So now I'm just putting that in its place here. So that'll be n minus 1 times n over 2 right here. Just simplify all of that like it is. You got a 2 times 2 is 4, n on the top times n minus 1 over 2n squared on the bottom. Okay, that's probably what I'm going to ask you to find, like on the practice set, something like that. It may be simplified from that as well, but that's what I want you to find on the practice set. But let's keep going here. We know that we could simplify that further down to 2 times n minus 1 over n, which is just 2n minus 2 over n this time. Remember the last one was 2n plus 2, example 1. So that is going to be equal to, and let me just box this right here, kind of running out of room here. 2n over n is 2 minus 2 over n. What happens as n approaches infinity? All of that goes to 0 again. What do we get for an answer again? 2. Riemann sums, whether they're from the left or the right, as n approaches infinity, they should converge. If they're true Riemann sums, they should converge to the same solution. Here, that's what happened. The left sums converge to 2, the right sums converge to 2. Left sums are a bit more of a challenge than the right sums, so in the practice sets, we'll only do those with just simple linear equations like in x. So they'll follow a similar pattern to this example, of course. Problem 3. Use right sums to find the exact area under f of x equals x squared. So a quadratic relationship this time, and you know from lesson 23 you've got a sum of x squared. That there's a formula that goes with that. Same with sum of x cubed. That's what we'll do in the next example. On that interval 0 to 3, n approaches infinity. So same idea here, and just kind of speeding the process up a little bit here. We know we're applying the limit definition. Let's just write that down. Limit as n approaches infinity of, what's our delta x this time? b minus a over n, 3 minus 0 over n, 3 over n. We know we can factor that delta x out of the summation, the f of x delta x summation. So we say 3 over n sum I equals 1 to n. This time it's x sub I squared, right? Now, just like in the other two examples, we know that sum of xi part, that's what we want to work on now and just see what that equals for our problem here with a delta x of 3 over n. So this time, let's just work on that. Let's work on it over here. Sum of xi squared from I equals 1 to n. So our first input is going to be 3 over n. That means our output is 3 over n squared. And then the next one we move over, we add a delta x on, right? That's our location. It's at 3n plus 3n. So it's at 2 times 3 over n. And I meant to say 3 over n plus 3 over n. That's squared. So be careful on that. Think about it. You're moving that over another delta x. So the input is 2 times 3 over n, and the output is 2 times 3 over n squared. And so then the next one would be 3 inside parentheses, 3 over n, that squared, and so on and so on and so on. Example 40.1, 40.2, next thing we did was we looked for that pattern, and we know it's going to be an x squared pattern here, right? And so factor out a 3 over n squared, because it's a squared pattern. And you can, right? It's 3 over n, or actually, what is 3 over n times 3 over n? That's 9 over n squared, right? That's what we're factoring out. And then times 1 plus 2 squared. So in other words, 1 squared, just to keep the pattern going there, plus 3 squared plus dot, dot, dot. So in other words, that is 9 over n squared. Sum x equals 1 to n of x squared. What's the formula from lesson 23 for sum of x squared? It's kind of a long one. That is 9 over n squared, parentheses, that summation n times n plus 1, that summation formula. Amazing that we can do that whole series, an infinite series, even if n approached infinity, which is what we want to do eventually here. All of that is just one formula here. All of that over 6. Now, this whole thing right here, that is this, right? Keep going. Now find the limit. Everything's in terms of n now, as n approaches infinity, of 3 over n times 9 over n squared times this whole thing. I'll just put that in parentheses again. N times n plus 1 times 2n plus 1 all over 6. Now keep working on this simplified sum. We have a 3 over 6 is 1 over 2, so we can have a 9 over 2 there. And then we have an n times n squared in the bottom there. That's n cubed. So we could say 9 halves times n times n plus 1 times 2n plus 1 all over n cubed. One of those n's is going to cancel, right? So we have an n and an n squared right there. And so that, we could simplify that to 9 halves times, expand out n plus 1 times 2n plus 1. That would be a 2n squared plus 3n plus 1 times 1, 1, all over n squared. That part we could simplify, 9 halves, and then what we're trying to do here is get it so we can have all the n's in the denominator and then set that equal to infinity. So 2n squared over n squared is just 2, plus 3n over n squared is just 3 over n, plus 1 over n squared, nothing cancels there, 1 over n squared. Now that right there, that's probably where we would stop, like on the practice set, and I'd ask you, which one of these choices is the summation, is the infinite series that results, or the infinite series formula that results. Do you see that? Do you see how as n approaches infinity, 3 over n, 1 over n squared, those would both go to 0. We'd be left with 9 halves times 2 equals 9. That's our answer. That's our exact area. You could do that on a graphing calculator if you want to confirm that, but that's what it would equal, is 9. Exactly 9. Let's do one more. Write sums, this time for x cubed. Look at the interval, 0 to 2. That means b minus a over n is going to be 2 over n. And same idea, same process as example 40.1, 40.2, 40.3. So here, let's just write out our limit definition. Begin it like we did example 3. Limit as n approaches infinity of, factor out that delta x, 2 over n. That's what it equals this time. 2 over n. Sum I equals 1 to n of x sub I cubed. What is sum xi cubed? What does that equal for I equals 1 to n? That's what we want to think about now. Well, xi, our first input with right sums, that would be delta x is 2 over n. So that first input is 2 over n quantity cubed. And then the next one would be 2n plus 2n, or 2 times 2 over n. That is cubed, plus 3 times 2 over n. That whole thing is cubed, and so on, and so on. So that means we could factor out a 2 over n quantity cubed, and end up with 1 cubed plus 2 cubed plus 3 cubed, so on the inside. So we end up with 2 over n, which would be 2 over n cubed is 8 over n cubed, parentheses sum x equals 1 to n of x cubed. What is that formula? Remember that one? It's simpler than the x squared one. That's going to be 8 over n cubed, parentheses n, and I'll put a brace around all of this, n times n plus 1. It's just that n plus times n plus 1 over 2. It's the sum of x formula, the whole thing squared, right? Remember that? That is what this part is. So now we rework our limit, and I'm not going to write limit as n approaches infinity, and I'll assume you know that's what I'm doing here. 2 over n on the outside of that. Now the sum of xi cubed part is times 8 over n cubed. What is n times n plus 1? That's n squared plus n, right? So it's basically, it's this whole thing, n squared plus n over 2, that quantity squared. Rearrange some things here. 2 times 8 is 16. And then in that parentheses part, you have a 2 squared on the bottom. So that's a 4. Let's just put the numbers together. 16 over 4. And then times n squared plus n, quantity squared, over n times n cubed is n to the 4th. Okay, so let's simplify that a little bit more. We know that 16 over 4, that's going to become a 4. And so we'd have 4 times n squared plus n times n squared plus n, which we could expand all over n to the 4th. And so that's equal to 4 times n to the 4th plus 2n cubed plus n squared, all over n to the 4th, which that would simplify down to 4 parentheses n to the 4th over n to the 4th is 1, plus 2n cubed over n to the 4th is 2 over n, plus n squared over n to the 4th is 1 over n squared. So all of that right there on the practice sets, that's what I'd want you to find. Not the exact answer. You can keep going with this. It's super easy to keep going with that, because the 2 over n, the 1 over n squared, by now you know those are going to go to 0. You're left with 4 times 1 is 4. That's the exact answer. You can check that on a graphing calculator as well. To show that you know how to do this and know what you're doing, then you need to be able to show that in your practice sets. And so that's why I want you to do the in terms of n part there. That's what you'll be asked to find on the practice set. So now you've used 3 infinite series formulas from lesson 23, sum of the x squared, sum of the x cubed, to find exact areas under a curve over a given interval. That a summation of a polynomial simplifies to a formula like this one, n times n plus 1 over 2, that squared for x cubed. That's amazing that we can do that, and that somebody discovered that. That we can use a formula like that to find the exact area under a curve over a closed interval. That's an even more amazing thing. And that is all for lesson 40.